In this lab, I observed an object, in this case a car, moving at a constant velocity over a certain period of time. Through the observations, I was able to obtain the car's approximate mass and its starting velocity. Using Newton's second law, I am able to relate this to the forces acting on the object. I put this video into Tracker in order to tell what the constant velocity of the car was and to track the object. I tilted the axes in order to make it as much like the car was moving straight across the x-axis as possible. If I were to flip the axes and make it so that the car was moving along the y-axis, it would not change any of my discoveries at all. The only thing that would change is which axis the car was moving along. If I were to make it so that the car was moving in between the axes, so not straight on the x-axis or straight on the y-axis, it also would not change the final product. The car would still be moving at the exact same speed. The only difference would be how we are looking at the car moving. As you can see, because the car is moving at a near constant velocity, this means that the change in velocity is zero. And as such, the net force acting on the object must also be zero. Using this fact, I was able to create a computational model of the car. And using this, I am able to predict where the car will be at any given moment, assuming that the net force on the object does not change. When I was creating the computational model at first, I used an extremely small difference in time in order to determine the initial velocity. However, when doing this, the computational model was far off from where I had expected it to be. This is mostly due to human error when inputting the data into Tracker. So in order to fix this, I used a larger time step for the initial velocity, how far the car had moved in approximately 4/10 of a second. In doing this, I came up with the chart you see here, which is a much better representation from what it was to start with.